I'd like to talk to you more about my new religion. It's called Grapheme. It also could be called Digamma if you want. Now, the focus of this video, besides Jingle Bells, is on the Digamma function. Now, what is the Digamma function? Well, before we talk about the Digamma function, we have to talk about the gamma function. The gamma function, gamma of x, is an extension of the factorials to all real numbers, and in fact, all complex numbers, except for negative integers. Actually, non-positive integers, since it's undefined at 0 as well. It's very useful for certain types of statistical distributions. It's used all over number theory, and it's a very important function. So when the user types in gamma of x into Grapheme and then requests the derivative, what is the derivative? Well, the derivative is actually the digamma function times the gamma function, because the digamma function is defined to be the logarithmic derivative of the gamma function. So this is the definition of the digamma function. Now, we want to be able to compute this numerically. And this is not the easiest problem to solve. It's also not the hardest problem that I've faced yet. But it's kind of cool. The techniques that are used, I think, are pretty interesting, and they're sort of thematic in the realm of numerical computation. So here are the three equations that we have to use in order to compute digamma. First of all, this is a recurrence relation. This is actually derived from the recurrence relation of the digamma function, of the gamma function, because it's like factorials. It's just how when we say x factorial is x times x minus 1 factorial, this follows from the corresponding law for the gamma function. Then we also have a reflection formula. This allows us to define the digamma function via analytic continuation into the entire complex plane. So this definition actually works for all complex numbers x, but this series that we're going to get to only converges for real of z greater than 0. So what we can do with this is, if we rearrange this equation, we can get gamma of z, or digamma of z, is pi cotangent pi times z minus c of 1 minus z, digamma 1 minus z. Now, if we plug in something like -5 into this, then 1 minus -5 is 6. So we can convert values of digamma whose arguments are less than like the real number 0, whose real part is less than 0. We can convert them into ones where the real part is positive, so that we can use this series. Now this series is kind of fun. It's digamma of z is natural logarithm of z and then minus an infinite sum. And the terms of the sum are the absolute values of these numbers gn, which are the Gregory coefficients. I also had no idea what the hell those were, so I did some research. But these can be computed and cached. They don't have to be recomputed every time. Basically, they're a recursively defined series of coefficients times n minus 1 factorial, and then divided by the rising factorial z sub n, which the rising factorial zn is z times z plus 1 times z plus 2 ... up to z plus n minus 1. So that's all fine and dandy. The issue is if we just evaluated this series numerically, say the first 15, Grapheme does the first 15 terms of the series. The issue is that while that will work well for large input z, because if z is large, then the rising factorial of z gets very big, and so the denominator gets very big, and so the terms get very small, so they converge quickly. But if z is close to 0 or close to 1, then the terms converge much more slowly, so a lot more terms are needed. But what we can do is we can use this recurrence relation to transform, say, digamma of 1 into digamma of 2 minus 1 over 1. And then we take digamma of 2 and convert it into digamma of 3 minus 1 over 2, and so on and so forth. So the way that it actually evaluates the digamma function for positive numbers, or for numbers with a real part greater than 0, is we use this recurrence relation to make sure the real part of the thing we're evaluating is greater than, I think it's 20 in the code. And then once it's sufficiently big, we calculate the value of digamma using this series. And we use, like I said, the first 15 terms of the series, and it converges pretty rapidly. Now, the last thing to keep in mind is if the real part of z is less than 0.5 or 1/2, we use the reflection formula to convert that value of z and evaluate digamma at a z value whose real part is greater than 0.5. So that will make sure that this series will converge. So yeah, that's how we evaluate the digamma function. For most values of x or values of z, it seems to give about 10 to 15 digits of precision, which I decided is good enough. Of course, the code could be very easily changed to allow for more precision, but that's not on my bucket list right now. Maybe someday far in the future. But yeah, that's the digamma function, that's Grapheme, and that's Jingle Bells.